Hello everyone, welcome to this video. My name is Amir Senahari. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to estimate soil moisture using Sentinel-2 images. It is very popular tutorial among remote sensing users. And now I'm going to show you how we can calculate the soil moisture using Sentinel-2 images with a spatial resolution between 10 to 20 meter. Let's go through this. In the previous tutorial in my YouTube page, I showed you how we can use Landsat images and OPTRAM algorithm to estimate the soil moisture with 100 meter spatial resolution because of thermal infrared bands in the Landsat data. But now in this tutorial, I'm going to show you if you were working with a kind of satellite data without a thermal band, how you can estimate the soil moisture based on the relationship between visible and also the SWIR or short-wave infrared portion of electromagnetic spectrum. So, same as previous tutorial, I'm using the same reference that is published in the remote sensing of environment and also totally is valid. And here you can see in the previous tutorial I showed you how we could estimate the soil moisture according to the relationship between NDVI and also LST or land surface temperature. This equation number 5 was our target, and also based on NDVI and land surface temperature I showed you how we can estimate the soil moisture. And also the OPTRAM model works according this inverse relationship between the NDVI and also the LST. But in this tutorial, I'm going to show you if we were working with a kind of satellite data without thermal infrared band, such as Sentinel-2, how you can estimate soil moisture. The OPTRAM model is based on the relationship between STR index and NDVI. STR is a kind of equation or spectral indices according to SWIR relationship that showing that highlighting the amount of moisture in our study area. After thermal infrared band, the short wave infrared is highly sensitive to the moisture content in the vegetation and also in the water and also in the soil. And in this tutorial, I'm going to show you how you can calculate the soil moisture with Sentinel-2 images using STR and NDVI. Let's go to the Earth Engine code editor platform. I'm very excited for this tutorial because it's very helpful for the soil moisture estimation. So, same as the other tutorial, first of all, identify your region of the interest. In this tutorial, I'm going to select a part of my own country in the northwest of Iran that's covered by the agricultural area and also the water areas and water bodies, and also with enough precipitation during a year. So here, through drawing tools available here, you can select a drawing, one of them to draw your study area. For example, I'm going to use the geometry tools here for the rectangle tools here to draw a geometry. And the geometry created with the geometry name, and also you can see that in your own code. And then start to type to write the program with map.centerObject to make a focus on your study area through the geometry. So in the next step, I'm going to call Sentinel-2 images. Make a new variable for Sentinel-2 images equals to the Sentinel variable equals to. Through the search places and dataset, you will be able to go through the satellite data available in the Google Earth Engine environment. So here, just type the Sentinel-2 images. 2 products appeared. There is something wrong here. Sentinel-2. Yes, there is. This is Sentinel-2 images, 2 collections or 2 kind of products about Sentinel-2 available. One of them is level 1C and the other one level 2A. The level 2A data is a kind of satellite images that is totally corrected atmospherically and radiometrically, and no need to do any kind of radiometric correction. It's included the surface reflectance values for the visible and infrared region of electromagnetic spectrum. But the another product, level C1, refers to those of Sentinel data showing the reflectance affected from the top of atmosphere or top of atmosphere reflectance that is not suggested for the spectral analysis works. For example, in this work, in our tutorial, I'm gonna use spectral indices to calculate the soil moisture. As long as I'm going to use spectral indices, I have to use atmospherically corrected data to get the most accurate estimation for the NDVI and also the soil moisture and STR index. That's why I prefer to import the level 2 data in the Earth Engine platform. So next, assign the image collection to the Sentinel and then throw the filter bond because of framing structure in the Sentinel-2 images. We use the filter bonds to bond our data to the selected region, and the region already called using the geometry here, and then through the filter date set the start and end date for the time extent we want to do process. So the start date is, for example, 2020 and the end date is 2021. So there is. And in the next step, I'm gonna call those of Sentinel-1 images included less cloud cover, for example, less than 45% in each frame. So make a less than filter through the Earth Engine.filter.less than from the properties available in the Sentinel-2. One of them is cloudy pixel percentage. Cloudy pixel percentage, just like that. I want to use those of Sentinel data in which cloudy pixel percentage in each frame is less than, for example, 45%, because I'm not gonna remove all the existing images for this period. Just I wanna remove those of images that highly covered by the water, by the cloud. Sorry for my mistake. And then print the variable to see how many Sentinel-2 images available for this period. There is something wrong here in Sentinel writing. Again, write and run the code. And remember to save your code because maybe we face with some kind of problems such as not responding or something like that. That will remove the whole of your code. And also, I highly suggest you to save your code before doing further analysis after each step is done. So, as you can see, for the selected region in 2020, more than 500 images available. And there is one point, and it is the Sentinel-2 images provided smaller image frames compared to the Landsat data, and that's why our region covered by multiple frames. So, and also in this case, I'm gonna convert the Sentinel images from, for example, weekly temporal resolution to the monthly. And also when I wanna convert them from weekly to monthly by getting average for each month, I will be able to make a mosaicing to merge all the mosaics into a single frame that helping me to make a single image for each date that is covered my whole of area, because maybe some of the existing frames only covers a small portion of my region of interest. That's why I'm gonna make, for example, 16 days temporal images or monthly data, and that's why I'm gonna do that. So to do this, to convert the weekly data, Sentinel with 6 or 7 days temporal resolution to monthly format and mosaicing same time, we need to use temporal collection function. If you followed my tutorial in my YouTube channel, definitely you know about the temporal collection function. But now, if you don't know about it, I will show you how you can write it in the Earth Engine that it is already developed by the Google developers and shared on the net, and also I'm using the function here in this tutorial. It is not my own. Actually, I'm borrowing this code and also sharing with you in this tutorial that helping you to make a multi-temporal collection in the Earth Engine platform. So that's how we can do this and make a new function here. The function name is temporal collection. We are making a new function, and you can set any name you want for the new function. The temporal collection including couple of arguments. The first is the collection, and referring to the input collection of data that we want to use in this function. And the next is the start date, and start will be referring to the start time in which we have the data. That will be 2020 in this case. So, and the next one is the count, referring to the number of images that we expect to have after running the code. For example, for 1 year, I want to make monthly images. As we have 12 months for 1 year, we will set count as, for example, 12 or replace it by number 12. And the next is the interval, is the delta time between first and second image, and also the last one, and the last is the unit of time that we want to use for the temporal collection analysis. These are the input arguments for the temporal collection function. And now in the body part, I'm going to show you how to combine these arguments into each other to make a unique body for the function to do the desired calculation. So in the first step, make a new list of sequence equals to earthengine.list.sequence. We want to make a list for the output images, and this list is starting from 0 to the number we set for the count, earthengine.number for the count. Sorry, earthengine.count. And as we are starting from 0, the count should be subtracted from 1. For example, imagine that we want to have 12 images for the output for each month, 1 image. So the list should be started from 0 to 11, because the count is from 0 to 12 we will have 13, and also to remove 1 we need to use a 0 to 11 actually in this case. So because and next, another variable is about the origin date. The origin date helping us to convert the string value for a start converted to the date format. That's very helpful. So now to do the further processing, we need to return the list as an image collection and do the next processing on each row separately. Return function returning one image collection that's returning the list of sequence with collection format. And now to do a unique processing in each row, we need to make a loop through the map, and then in each row we make a function that each row considered as an I to calculate the start date and end date. This part is very important. The start date and end date, because for each period that is defined by the start date and end date, we need to get an average or median. So start date from origin date like that dot advance. So here to go forward, we need to consider a delta time here, and delta time already identified through the interval argument. Interval argument dot multiply. So dot multiply to the number of row we are doing process and keep the unit same and do the same calculation again for the end date with a little change. I'm selecting this part and pasting for the end date, and as you can see, just we need to go 1 unit after start date. To do this, make a little change here. Earth engine dot number I dot add 1 to go 1 unit after what we had in a start date. So finally, the function returning the input collection in a period of time that is identified through the start date and end date. Start date and end date. And for this period, I want to get the median value. Why median value? Why not average? Because median, unlike the average, median less affected from the extreme minimum and extreme values that may occur because of the shadow and because of the cloud cover in the pixels. So I'm gonna get a median in each pixel from surface reflectance values recorded in the available images with the cloud cover less than 45%. So in order to be able to do the further processing in the next step, I suggest you to use to set a system time start and system time end for the next parts. So that's set. The first property is system time start, and here we will have the start date with millisecond format. So, and then set a system time end. Another important thing, another important property, system time end. And here we have end date dot millisecond. Just like that, it's very easy to use. Definitely writing such kind of codes and working with such kind of functions, it is not easy to use for the beginners, for the Google Earth Engine beginners. That's why I suggest you, if it is difficult for you, just copy this function and paste it into your own code in the first step to learn how it works. And after learning, if you want to continue learning process in the remote sensing and Google Earth Engine, try to learn such kind of function process because it is very, very applicable in the Earth Engine data analysis. And in all the projects, couple of times or several times I'm using temporal collection without any doubt, and definitely you have to use it for the variety of for the various applications in the Earth Engine platform. So, and also I will share you my code in the below video in the description box in the YouTube channel, and you can pick it up and compare yours with mine, and also to find the errors. And also if you couldn't solve the problems or existing problems, you can reach me out through the YouTube channel and share the idea. I will try to help you. So back to the programming. Where were we? So now I'm gonna make monthly Sentinel data. For each month, I want to make a cloud-free image for each month that is covering whole of region using the temporal function. So make a new variable, for example, the monthly image equals to, so we created the temporal collection with these arguments in the code, and now copy and paste it, and also just replace the existing arguments with the existing variables and also the criteria you have considered for your project. For example, instead of collection, we will have Sentinel data, and a start date should be equals to the start date for Sentinel variable, that is 2020, and the count refers to the number of output expected. As we want to have 12 one image for 1 month, here the count will be 12. An interval, the time difference between the first or delta time, referring to the delta time between the first and second image. As we want to produce the 12 image with 1 month interval, the interval should be 1 and unit should be months, just like that. So now I'm printing monthly and run it. In the right panel, there is 12 elements available here. So as you can see, for each month, we will have one single image with the low cloud cover, and as you can see, all the bands available here. So in the next step, back to the reference, and here you will see that for the soil moisture, first we need NDVI and STR. All of you remote sensing users knows about the NDVI and how it works. The NDVI refers to the normalized difference vegetation index that highlighting vegetation cover in the study area, and also showing the different and also helping us to differentiate vegetation cover according to the health condition and also density, and also the various factors such as chlorophyll, and on it goes. It's one of the most famous and most applicable indices in the remote sensing that we are using here. So, and another one is STR index. It is calculated based on the SWIR band according to this relationship. And now in this step, I need to calculate the STR and NDVI for each date separately, because these are the key components for the soil moisture estimation using the OPTRAM model. So now in the next part, I'm gonna make a new variable here as parameters. Parameters referring to the parameters needed, essential parameters needed for the soil moisture estimation. Parameters equals to get the monthly data and then through the map make a new function. So each input image in the function consider it as an IMG, and now make a new variable as bands. In this variable, I'm gonna select the existing bands starting with B. If you want to know about the band's name or band's information, go to the band's data, go to the data image or collection description. Under the bands menu or tab, here you can see the band names and scale factors and spatial resolution and the wavelengths. That is really important. So first of all, I'm gonna select the real bands starting with B, and no matter which number. So back to the code, and here through the dot select, as I mentioned earlier, you will be able to select the existing bands starting with B or real bands. And to apply the scale factor, use dot multiply to change the range of values from the original range to the surface reflectance values, just like that. In the next step, make a new variable for the NDVI. And as you know, the NDVI referring to the normalized difference vegetation index and calculating according to the relationship, normalization relationship between the near infrared and red region of electromagnetic spectrum. Here I'm getting bands, and then through the dot normalized difference, I'm gonna get normalization relationship between band number 5 and band, here in the Sentinel-2 images, unlike the Landsat, the near infrared band using for the NDVI is band number 8, and also the red band for the NDVI is band number 4. And so unlike the Landsat, here I'm using band number 8 and band number 4 to calculate the NDVI, and then rename the band to the NDVI. After NDVI calculated, make a new variable for another essential factors needed for the soil moisture estimation in the OPTRAM model, it is STR equals to, from corrected bands. Here I want to write an expression. I'm gonna write the equation using expression function here. So back to the reference, here you can see that the STR is based on the SWIR, and also the SWIR could be this region 1650 nanometer or 2210 nanometers, and also you can select or you can pick your bands according to this region. But because of shorter wavelength, longer wavelengths in the shortwave infrared have more sensitive are more sensitive to the soil moisture or the moisture content, I highly suggest you to use a 2000 nanometer region for the soil moisture estimation if it is available in your dataset. Hopefully, when you are working with Sentinel-2 images, 2000 nanometer is available in band number 12 with 20 meter spatial resolution. So the band 12 here selected as target band for the calculation. Here we have one numerator and denominator here. In the numerator, if you check the equation number 7, there is a subtraction between 1 and SWIR. So here, in this subtraction, 1 subtract from SWIR, and then 2 power 2, just like that. And also in the denominator, there is 2 multiply RSWIR, 2 multiply RSWIR. Here is SWIR, the only one band involving in the calculation. So SWIR is an unknown variable in the equation. So we need to define a known variable instead of the SWIR. SWIR equals to, from the corrected bands that select the image with the band number 12, just like that, and rename the output as STR for this equation. So finally, if you when we want to have NDVI and STR for each date, make a new stack layer equals to, using earthengine.image.stack, you will be able, so image.stack, I'm trying to find image.cat, sorry, it was my fault, image.cat, helping us to stack NDVI and STR into a single image, and finally the function returning the stack image with the properties of input images. And copy properties is very important because helping us to do the time series analysis using system time start and system time ends in the next step. So here, to see the to see if the code working well or not, just print the parameters. If there is any syntax error in the code, in the console, you will face with a kind of error. But this time, hopefully, code works well without any issue in the programming steps. So for each date or each month, 2 bands available. One of them is NDVI and the other one is STR. So after calculation of essential components or variables in the OPTRAM model, now we can go through the further calculation to find the next criteria and items. As you can see, there is a linear relationship between the STR and NDVI, and in this relationship or direct relationship between these, or positive relationship, and here, as you can see, those of NDVI values, all the NDVI high NDVI values, you can see that pixels locating in this region showing the higher moisture content. Actually, the STR is a kind of is a moisture index that's showing high moisture and lower moisture according to the equation we mentioned. So higher STR values referring to the higher moisture and lower STR values referring to the lower soil moisture. To estimate IW, SW, and SD and all other criterias, first we need to get STR values for full vegetation cover and for the bare lands. Here we have a two-dimensional plot. In horizontal axis, you can see the NDVI ranges from 0 to 1, and also all the pixels ranging around 0 in the NDVI showing the soil, and all the pixels with value around 1 showing the full cover vegetation cover. So, and now first we need to make a threshold to separate the full cover and bare land in the STR images. So to do this, I'm making a new variable for STR full cover, just like that. STR full cover equals to, from parameters calculated in the previous session, I'm making a new function to select the STR values for the full cover regions. In the function, each input image considered as an IMG, and here first using NDVI threshold, we are making a threshold for full covers. Threshold full equals to, from each input image, select the NDVI image. In the NDVI, usually pixels greater than 0.3 showing the full cover regions. So now I'm gonna mask STR image according to the full cover threshold. So a new variable, it is STR full. From input image, select the STR band and then update mask. Use the masking process to remove the non-full cover regions according to the threshold that is identified in the last line. So for each date, STR full cover, STR full will be returned by the code. So the function returning STR full cover, just like that, with the properties of input images. There is. And now in the next step, I'm gonna use I'm gonna calculate or separate the STR values for the bare lands. So to do this, make a new variable. So the STR full cover here showing the STR values for this part of relationship, because the NDVI is greater than 0.3, covering all the pixel for this part, and also this is STR for the full cover. And now I'm gonna calculate the STR or estimate the STR values for the bare land. Values, for example, from 0.2 to 0 or less. So here, make a new variable STR bare land. STR bare land equals to, from input parameters dot map, make a new function, each input image as an IMG, and now we need to make a new threshold for the bare land. So threshold for bare area equals to, from input image, select the NDVI, because NDVI is a global index and helping us to separate water, vegetation, and soil for all around the world with well-known threshold values. So, and then I want to select the pixels between 0 and 0.2. So pixels greater equal than 0, and I want to select from ndvi dot select from ndvi those of pixels are less than 0.2. So this region usually showing the bare land or exposed area, and also with very low vegetation cover or sometimes no vegetation cover. So, and now we want to mask the str image based on this threshold. The new variable is str-bare equals to from input image select the str index and then mask the non-bare land region through the update mask function thr bare land. So function returning str for bare land with the properties of input images img.property names. So as you can see, str for full cover and bare land calculated, the str values for this region and this region calculated. And now we have 4 corners in this relationship. That is really important. So actually there are 2 lines here that's showing the wet edge and dry edge. To calculate the wet edge, we need to have the value for this side or this corner and this corner. So, and now I'm gonna show you how we can calculate these items. So first I'm gonna show how to calculate this corner and this corner, because in the str full cover if you get the maximum value and the minimum value, you will have the wet vegetation cover and also the dry vegetation cover. So let's go to see how it works. So in the first step, I'm gonna show you how to calculate wet vegetation cover. The wet vegetation cover is this corner, and also here it is vegetation because ndvi is around 1, and also this is wet because it's showing the higher str value. So wet vegetation cover equals to str full cover dot max, and then because it is a time series, we need to get the maximum value for these images for the str full cover, and then we need to get the maximum value in the maximum image through the dot reduce region. So through the dot reduce region, the reducer here, the reducer equals to Earth Engine dot reducer dot max for the geometry that is selected already as the geometry, and the scale is very important. Most of the time, if you set the scale to the numbers such as 10 or 20 because of spatial resolution in the Sentinel-2 images, definitely for the big regions you will face with the user memory limit exceeded or some kind of limited number of pixels for processing or some sort of errors in the Earth Engine. That would be better to reduce the scale value from 10 and 20 to 100 to avoid such kind of errors in the processing steps. In order to get the output as a value, use the values and get the first item in the conversion. And in order to convert it to a number format, and here Earth Engine .number is very helpful. So the wet vegetation value that is showing the values that we have for this site. For this site, and now if I get str bare land, the minimum value for the str full cover calculated, the minimum value will be equals to this side of relationship. So again, I'm gonna repeat this process with a little change. As you can see here, let me to make a bigger space for the programming, and also it is easier for you to see. So now I'm gonna select or estimate the dry vegetation value. Again, str full cover, because in the vegetation cover I'm gonna find the driest value or the lowest value. So that's mean the minimum value, and again instead of that max I'm using that min again. So, and also this is dry vegetation cover. So in the other side, there are two important points that are calculated. So one of them is IW and another one is ID. The IW is the highest value in the STR, this side. So, and now STR bareland here, STR bareland showing pixels in this part, and also if you get the maximum value, it would you can get the this corner value or as IW, and also if you calculate the minimum STR for bareland, you will have the value of dry soils as ID here. So just I can copy and paste the previous code with a very little change. Here, instead of the VD, we will have IW or wet barelands. Here, wet barelands equals to, instead of str full cover, now you need to use str bareland here, str bareland, and because we want, and also as we want to get the wet barelands, the maximum value should be estimated here. Instead of min, I'm using max here for the IW, and use the same code with a little change, but this time with minimum value to get a dry value for I. ID equals to, instead of max, we will have that min. So, 4 corners calculated in the OPTRAM model, and now we need to estimate the wet edge and also the dry edge. The wet edge and dry edge calculated according to the differences between this corner and this corner, this corner and this corner. So for the dry edge and also here for the wet edge, make a new variable here, SW, the slope of wet corners equals to the here we need to subtract the wet vegetation from the we need to subtract the wet vegetation from the wet bareland. VW dot subtract from IW, and also for getting a slope of forget the slope of dry region, the vegetation dry that subtract from ID, just like that. And now, as you can see, if you go to the equation, all the parameters SW, SD, IW, and ID, all of them calculated, and now we want to we can apply the equation number 10 to get the soil moisture value here. So just make a new variable. This is the soil moisture equals to get the parameters image, because in the parameters collection we have the essential variables NDVI and STR that is changing during the time. So from the parameters, make a loop through that map, and for each image we want to apply the equation using a function. So the index for the soil moisture equals to, use the input images and dot expression function to write the equation. In the equation there is a numerator and denominator, and that are divided. So here in the numerator, write or type ID plus SD, ID plus SD, multiply NDVI, subtract from the STR value, subtract from STR images. So in the denominator, the ID subtracts from IW, the ID subtracts from IW plus to the subtraction between SD and SW, subtraction between SD and SW, and multiply to NDVI value, and multiply to the NDVI value. So in the next line, I need to define or introduce each variable for each unknown variables I'm using here. For example, ID should be equals to the ID that is calculated before. SD equals to the SD that is calculated before. So the NDVI and ST are coming from each input images. So, and here the NDVI come from each input image. Select the NDVI. Only the NDVI and ST are changing, and they are time dependent. And as long as NDVI and ST are changing during a time, you will have different soil moisture using these constants calculated. So this is the NDVI, and also for the STR is same, equals to from each input image that selects the STR value, and then IW should be introduced. IW equals to the IW, it is also calculated, and the next one is SW that is not defined yet, SW. So the output name will be dot rename. The output name is soil moisture, and the code returning the index with the properties of input images. So just like that. The soil moisture is calculated. I'm printing the result to see if there is any problem in the processing steps or not. Hopefully code working well. There is no issue. Just remember to save your code, and the image collection is under calculating. And remember that here we are combining this equation, the final soil moisture image calculated using combination of 10 meters and 20 meter resolution. And definitely the spatial resolution for the output is not only 10 or 20 meter, it is something between 10 and 20, maybe 15 meter is the mid range of spatial resolution that we will have for the output. So here, as you can see, one soil moisture image is available for each time, and also as long as you have the input properties or system time start values, you will be able to plot the time series values here. For example, I'm gonna select a point in the region to see how NDVI values change for a point. For example, this is my selected point, and in this region, I'm gonna print the change of the change of soil moisture values through the user interface chart function. User interface dot chart dot image dot series, helping me to plot the soil moisture value for the second location that I marked, and also for each date. In each date, I want to get the first value from this point through the reducer dot first, helping me to get the first image, and the scale should be equals to, for example, 20 or 15, and each property system time start. Run the code, and we are waiting to see the result. As you can see, this is the NDVI, this is the soil moisture value, but the range of value is very small. And also, if you want, if you want, you can add a constant value to increase the values for the output. So, but it is not necessarily But if you have a problem or working with a very small number of values, you can, for example, multiply, or you can add a constant through the multiplication to the output values, like 1000, to have a bigger values that is more meaningful for the interpretation. It's totally up to you. And also, if you want, you can add a constant to get a better interpretation about the range of values. And sometimes higher moisture in the region, we had the higher soil moisture values. If I select another region, definitely we will have some changes in the generated chart. As you can see, the generated chart changed according to the soil moisture changes. And also, if you want to see the visual soil moisture maps, it's very easy. Just use the map.add layer here. Using the map.add layer, get the soil moisture values, and also make a stack layer through the .2 bands, and then through the .clip you will be able to clip the image based on the regions we have selected, and the output will be soil moisture or SM name, and use the false at the end to avoid automatic visualization process. Run the code again, and here after a few moments you will see the soil moisture map that is created. And also, this is a multicolor image. You need to change it to a grayscale format. For example, the first image with the 90% contrast, if I increase it, you can see the soil moisture value. But there is one problem. The water body reduces the amount of contrast in the output images. And also, we can remove or mask the water body from the input image in this case to increase the contrast. As you can see, as long as we have the water body, the rate of enhancement or contrast strictly changed. And but using the another techniques for the visualization, you can see the better visual. You will have a better visual properties for the output. To remove the water bodies, it's very simple. If you have no access to the land cover products, no worries. Only using the NDVI image, we can make actually a mask layer for the water bodies and also the negative pixels. Here, for example, from the NDVI, I want to make a mask here. From the parameters, as you remember that from the parameters, here we had parameters. In the parameters, NDVI were available. So from the parameters here, only select the NDVI values. That's the NDVI band, and then make an average image for the NDVI from the NDVI images, and then you can set, or and also you can make this mask in the processing steps. For example, in the soil moisture estimation, I'm gonna make a mask here. From each input image, I'm selecting the NDVI, those of pixels that have lower values, the NDVI negative values showing the water content. And here, using the mask, I'm going to select the pixels that are less than 0 in each NDVI images, because totally they are showing the water area and also the water pixels, or minus 0.1 here, just like that. And then through the dots not, we can convert it. We can convert the mask to set the value number 0 to the water areas, and also the value number 1 to the rest of the regions. And finally, for each date, through the .update mask, you will be able to remove update mask. They'll remove the water content through the mask equation. So here you will have the final soil moisture value, but this time you can see that the water body is completely removed. So here, for example, in the first image, click on apply. Because of cloud cover, still we have same problem, and also some regions with a actually a small water content that is not detected in the NDVI images. And also, as you can see, because of heavy cloud cover in this region, the contrast reduced. But for the other dates with the lower cloud cover, I hope we got a better visualization process. Still the problem exists, but here if you increase the contrast, you will see the regions with the higher soil moisture with a brighter region or white color. For the times without the cloud cover or the water bodies, I think we could have a better visualization process. Let's see. Yes, for example, this is for the summertime and agricultural regions and the croplands with higher soil moisture showing with a brighter color, and also the regions with the lower soil moisture showing with the darker colors. Using the inspector here, if you click on each pixel, you will be able to see the soil moisture values in the winter times, and also the autumn times you will see the higher values, and also vice versa. Also in the croplands, you can see the soil moisture value changes according to the estimation methods. So if you want to download the final results, it's very easy again. Through the .export.image to drive, you will be able to get export from image into Google Drive. Some arguments are necessary for exporting process. The first one is the image collection. Soil moisture bands, soil moisture data should be stacked through the two bands and then clip it based on the region of the interest, that is geometry number 1. And the next argument is the description introducing the name of output GeoT file, that is soil moisture or Sentinel soil moisture. And pixel size scale is a pixel size for the output that should be 15 or 20. For example, I set the 20 because the still is good to get the soil moisture value with the 20 meter spatial resolution. And the region of the interest is equals to geometry, and the maximum pixels in each image finally should be equals to 1e13, and the CRS or spatial resolution, you can set the CRS or coordinate system. You can get the coordinate system code from the soil moisture stack value. So the soil moisture stack, if you use .getinfo.crs, you can copy the coordinate system of Sentinel image to the CRS argument. And the region, scale, maximum pixels, description, image, all of them introduced here. And also, if you want, you can set a folder for the output. This is Sentinel-2. I'm gonna make a new folder in my Google Drive to save the output with the Sentinel-2 name. Just like that, and run the code, and after a few moments in the task, you will have a new task. Through the clicking on run, the process of saving in the Google Drive starts, and after a few minutes that process is done completely. The label here from gray scale converted to the blue color, and then you can go to the Google Drive and download it. So I hope you like this tutorial, and I tried to show you the soil moisture estimation with the simplest strategy I know in the Google Earth Engine platform. And also finally, I thank you for your attention, and I hope you can use this code and tutorial for your own projects successfully.